one and we have
Yeah, absolutely. We can record and then I'll replace the link with the one from today instead. That's great.
uh, okay. Well, sounds good. Okay.
Yeah.
Yeah, we'll see. The tutorials are there as well. So anyhow, no problem. Welcome everyone, to the Ruby Data Academy on Wednesday. Hold on, let me start sharing here. There you go. So as I was briefly mentioning, we already had a session about this yesterday, but we're gonna repeat it today. My name is Andres Plazas Malagon. I work for Slack National Accelerator Laboratory, and within the Rubin Observatory, I'm part of the community science team. This year, as you know already, the Rubin Academy is focusing on beginner level use of the Rubin Science platform. In particular, we're focusing on Data Preview 1. We have 10 sessions distributed throughout the week. We're repeating some of these sessions at different times and during different days in order to accommodate everyone, hopefully. And we're also replacing some hack and networking sessions that we had in previous academies with Q&A questions. So after this session, there will be another one on visit images and source tables, and after that, we're going to have the Q&A session. But in case you cannot attend the session or just in general, I wanted to remind you about this very important website, which is the Rubin Community Forum. You can open an account whether you have data rights or not. It's free and fast, and this is a way in which you can ask us anything about Rubin and in particular about DP1 this week, of course. The Rubin staff are here to help. When you get to this website, you're gonna see there are different categories, news, but one category in particular is the support one that I want to highlight, in which if you post any questions there, the Rubin staff are going to answer or find you the expert that will help you find an answer to your question. And also, we encourage people to help each other in this community and to have answer questions that you may know from to other users to give answers to questions that other users have posted. Um, okay, yeah, so please use community.lsst.org. If there is a question that you have related to Ruby, it is very likely that somebody else also has it, so it benefits everyone in the community. I also wanted to point out that everything that we're talking about in this session and even this week is in the documentation associated to DP1. And this is the website dp1.lsst.io. We're also preparing a paper about data preview 1 that is currently in internal review in the project, but there is a draft that you can access right now with more details about DP1 and everything that we're talking about this week. So the link is there. This is a technical note. It's called Rubin Technical Note 95. So this is a documentation that this technical note has a DOI that you can use to cite it. And also every data set, the instrument, the LSSD COMCAM, they all have DOI, so please use them when citing the word like digital object identifiers. In general, the Rubin Observatory, we have also information in the Rubin Observatory website. This is another important website to keep in mind, and that's rubinobservatory.org. And in particular, please go to the For Scientists section of this website, and where you're going to find all sorts of useful information and also references on how to cite the Rubin Observatory in general. Today, we're going to talk about the deep coadds and the object table. And I'm gonna present a few slides, and then we're gonna go through a few tutorials from the portal aspect and the notebook aspect of the RSP related to accessing deep coad images or stacked images and the object table. I'm gonna explain a little bit about the data processes that went into the production of these products, the data products themselves, and then we'll move on to the tutorials. We're going to start describing some definitions, some key concepts. So the first of these are the concept of a sky map, tracked, and patch. A sky map is an all-sky tessellation grid that subdivides the sky into polygonal tracks and also patches. So for DP1, we have about 19,000 tracks. each covering about 2.8 square degrees of the sky. And each tract is further subdivided into a grid of 10 by 10 equally sized patches. And as such, each patch has a size of 0.028 square degrees, or 79 by 79 arc minutes. The object and there are also concepts about what an definitions on what an object and a source are, because the LSS uses specific definitions for these terms. A source is a detection in a single process visit image, and an object is an astrophysical object at a static sky coordinate. So the source table contains measurements made on objects in processed visit images, and the object table contains measurements made on objects in the deep coad images. So how do they produce these deep coads? So the image combination, the coadded images are created combining multiple calibrated individual images obtained in a particular filter and of the same region of the sky. So we're doing this, of course, in order to obtain a greater sensitivity or depth or signal to noise ratio. So we start by selecting our inputs. We put a cut on the quality, on the image quality, on the scene of the individual processed and calibrated visit images. And this cut for DP1 is of 1.7 arc seconds in the PSF full width of half maximum. Then, before doing the combination, we create masks in order to get rid of transients and transients objects and artifacts, for example, satellites or cosmic rays or defects in the detectors, so they don't get into the final coadded image. Then after that, we're going to co-register all the individual inputs. So we align them and then we warp them into a consistent pixel grid. And then after that, once they are aligned in this grid, we use a mean stacking algorithm that is weighted by an inverse variance map, in order to produce this combined image. We also do a residual background subtraction, which is just a subtraction of a constant background that is fit and subtracted, as I just said. So in the end, we end up with deep coad images, and for every single patch in all the tracks, for one patch we have a coadded image, a coad image. And this image is a calibrated image in flux, in physical flux of nanojanskins. We also do object detection and measurement. So we detect signal objects that with signal to noise ratio greater than 5. We have actually what we call footprints. And we have the concept of footprints because, as you can see on the image of the right, a footprint is usually made of a combination of blended objects. So we need to do the process of the blending, especially for the LSST, and for the depths that we're reaching, we have find a lot of blended footprints. So these footprints that have multiple peaks are blended into a set of child and parent, or children and parent and children objects. We use a software called Scarlet Light, which is a version of another software called Scarlet. The reference for that is Melchior et al. 2018. And then we do forced measurements, and then all the deep coad detections in at least one filter. And then the coordinates are fixed for doing these forced measurements. And these are forced measurements of PSFs and extended object fluxes, shape and size measurements. And we do this in all the 6 photometric filters of the LSST. So almost by definition, the force measurements could have a signal to noise ratio of -5, because we find the locations in the coadded images, and then we do the force photometry measurements, for example, in the individual visits. And well, in the end, we obtained the object table. So we've talked about the deep coad image, and then now we're going to have this other product, which is the object table. Um, so the data access. So how do we access the deep coad images? So we can use the Butler, which is like a high-level interface software that I will show you a little bit in one of the tutorials. You can also use the standards or the protocols from the International Virtual Observatory Alliance. In particular, we have a simple image access protocol or a table access protocol that you can use these services to access these images. So for the butler, for example, you need to identify, so the official name of the data product is deep coad, and then you needed to give it a minimum amount of dimensions in order to identify that data set, in which in this case, these dimensions are the band, the sky map, as I was mentioning before, the tract, and the patch. For in the language of the IVOAI, these images as well are what they're called calibration level 3. So in very general terms, calibration level 1 are raw images, calibration level 2 are visit images, and calibration level 3 are the rest, such as the quad images. So in this case, we're going to have about 2,644 the images, and the name of the table for the, if we want to use, for example, the portal aspect of the RSP, we're going to retrieve these deep coad images from this ivoa.obscore table. So these are the deep coad images are in a format that are called exposure F, which is like a particular class within the astronomical framework software that is used within the LSST science pipelines. But what it means is that these are a set of three arrays, and each array is a two-dimensional array. So the first component of the first plane is what is called the image plane. Is just the sky pixel data in flux of nanojanskins. Then you have another plane, which is called the variance plane, which gives us the noise in the flux in units of nanojanskin squared. And then we also have a mask plane, which is an integral bit mask, like the ones used in SDSS. We also have access to metadata. So, for example, these objects know the list of input visit images that went into creating this deep coad image. Once you have a deep coad, you also have access to a point spread function kernel. You also have photometric information on photometric calibration and information on the astrometric solution or the world coordinate system. So you can take a look at the schema in general of maybe for the tables. You can go to this website sdmschemas.lsst.io or also via the portal user interface. You can also access the schema in the notebook aspect of the RSP, and I will illustrate that in a moment. But yeah, so this is relevant, of course, the schema for the table. So here we were talking about the images, the deep coad images. Now for the object table, you can also access them via the table access protocol or the butler as well. But the general rule of thumb is we recommend people use the butler to access images and the tab service in order to access catalogs. But there are exceptions to that rule, but that's like the general recommendation. In the case of the object table, the dataset type is called object, and the required dimensions are sky map and tract, and it gives us an arrow astropy format object. If you want to access this table via the tab service, it's going to be called dp1.object, and it has about 1,300 columns, 1,272. So that's something important to know. That's why you can search the schema, and also is recommended when you do a query to just to do a subset of the columns in order to be more efficient. And then another point of notice here is that in this case for the P1, we're gonna have only 2,300,000 rows, but for the LSST, we're gonna have a billion rows. So it's good to be efficient in the spatial constraints and also in the column constraints when you're doing a query. And we're going to see that in a few minutes in some of the tutorials I'm going to show. So here we list a few key columns of out of these 1300 columns that are important, of course, like the unique identifier, the coordinates, the celestial coordinates, different types of fluxes in the nanojaskins, fluxes per band, magnitudes in the AB systems that are already calculated only in when you retrieve the table in the via tab. You have also extinction using the dust Schlegel map dust 98, that you have also shapes if you're interested in the shapes of objects, in this particular case, the Hirata, celiac, and Maldenbaum shapes, and a variety of pixel flags and quality flags that you were gonna have to figure out what you need to do in order to get a purified sample of whatever you need. So yes, so these are some of the key columns. So now we're gonna show a little bit of how we can do these queries or how we access these products via the Rubin Science platform. So here I wanted to show you first a way of displaying a deep coad using the portal aspect of the RSP. And before moving on, I was going to say I'm going to use this astronomy data query language, which is astronomy SQL, a way of doing it. So I just wanted to point out here that if I wanted to get the deep quad image, then of course I go to this table that I was telling you before, and then also specify the calibration level, data products, and image. And then I get a few of columns of interests, and asking it also to retrieve an image that it's close to or is centered around a particular field. I believe this is the center of the extended, oh yeah, it says right there, is the center of the extended Chandra Deep Field South, one of the 7 fields observed in DP1. So if you go to the RSP to data.lsst.cloud and then you go to the portal aspect, then this is the first thing that you see. Here, then I'm gonna go to this tab. Let me see if I can increase the size of this a little bit. Go to the DP1 images tab. This is the UI interface that you see first, UI assisted. This is one way you can play around with putting a location of an object, for example, of other types of options that you have that you can do here, and select and unselect the columns that you're interested in. But as I was mentioning before, I wanted to use the ADQL way of querying things. So it's right here at the upper right. Wanted to point out here that you can also see the schema here. There's a schema browser for all the data products, for example, the object table. Just wanted to point that out, that is there, in case you wanted to take a look. And also there are examples of predefined queries that you can see as, taking it as an example. But in this case, we have this query here to get the deep coat image, and we're just gonna copy paste. And we click search on the lower lower left corner, and wait a little bit while the magic happens, and there it is. So yeah, so this is pretty cool. The portal to take a look at the images using this Firefly system that is called the visualization software, and and there are several things that you can do here in the portal aspects. We do have tutorials about image displaying of the portal aspects, so I'm not gonna go a lot into details, but you can start exploring around here a little bit. For example, you can save the image, you can put some coordinates here. I think you can even measure some parallactic angles somewhere here. You can put a grid of coordinates. You can overlay bits, whatever you want. You can get rid of what you just put here. So there's a lot of cool stuff that you can do. See, here you can look at the table of what you retrieved, and then some charts here that in the next query, we're gonna play a little bit around with this chart. So, so yeah, this is just one way of visualizing these images. Just wanted to show you quickly how to do it with the portal aspect. Then another query, because we have a couple of tutorials to go through, another query that we can also do is now with the catalogs. So, or the tables, sometimes we say tables or catalogs. So we wanna now look at the object table. We're gonna retrieve just some magnitudes, some colors. I have to create some colors and the coordinates here. Again, this is the object table that we wanna query. We do a spatial constraint. As I said, it's always recommended to do a spatial constraint around the center of the same field, just a fraction of a degree in there, and then some coding magnitude as well. But of course, you can put whatever other constraints you want in here. So we can copy this and then go back to the portal. And in this case, we're actually gonna go to the DP1 catalog tab at the top, which looks very similar to what I showed you before. You have this UI assisted way of querying things. And again, you can do your spatial queries here, cone shape, etc. But in this case, we're doing the ADQL way of retrieving the table. So this is um, here using our tab service. Okay, and then it kept the image there, but then it changed the chart and the table. You can change the layout of what is shown here. If you look at this little hamburger icon at the upper left corner, there are lots of options here, but one of those are like the results layouts. If you just want to have the image and the charts, for example, you can do that. And actually kept the image because what we were doing is we were retrieving objects near the center. So yes, I guess I should have emphasized that. So this query is actually giving us the objects that are near the center within radius, this radius of the center. So yeah, so we have that. This is pretty cool. And in this chart, for example, if you go to details here, it can tells you a little bit about the explanation from the schema of whatever we told it to retrieve, some brief description. If you look at this gear icon here, for example, you can do some RMAG. Yesterday I was trying to do a color magnitude diagram, like let's use C model here. You can do a color magnitude diagram, GC model. Let's do G minus R versus R. And then you do apply just to show you very briefly the kind of things that you can quickly do. And then we have some version of a color magnitude diagram here for those objects. But of course, you can play around with more options and do something more refined. Yesterday, I was showing one of the cool things that I like from here is that it knows that the syntax is wrong, so it becomes is red if it's wrong, and then of course gives you the option of what the actual name is, and then it becomes black, and then it works. Okay, so that's great. So yes, I wanted to now. That was for the portal. Again, I encourage you to take a look at your own pace at the tutorials that we have prepared. So there are now, I wanted to look now at some of the tutorials on the notebook aspect of the RSP. Yesterday, I was looking at the deep coadds tutorial, but I wanted now to look at the object table tutorial, and if we have time, maybe at the survey property map tutorial. So again, you go to data.lsst.cloud, then you choose now the notebook aspect of the RSP. Then you'll see something like this after you select the software that you want to use and the size of the container. And one of these cool things that I really like is it's like a relatively recent addition, which is that you can go to this tab and it gives you all the tutorials that we have prepared for you. So before you had to go to the folder and look at them, but this is really handy here. And this is for the DP1, we have prepared several series of tutorials, and I really encourage you to just look at them at your own pace and give them to your students. And this is great. Yeah, I think so. So in this case, I said I wanted to show you the object table. So I go to data products, and then we go to catalogs, and then we go to the object table tutorial. And let's go through it slowly. So yeah, we have our tutorials. They all look more or less the same because we follow a set of standards to make them look the same and have a certain format. In this case, we're talking about the object table that, as I was mentioning before, it contains force measurements in all the photometric bands of the deep coad images at the sky coordinates of every source detected in either an individual visit image or in a deep coad image in any filter, as long as you have a signal to noise ratio greater than 5. And the object table contains only the blended objects. When I was talking about the footprints, so those are like the children and not the parent objects. Duplicates have been rejected as well. As I was mentioning before, the tab name of the table is dp1.object, and the Butler dataset name is object. We have 1,296 columns and about 2,300,000 rows. We have some related tutorials that you can take a look at, the 100 level series of tutorials, and there's also another 200 level tutorial on looking at deep coad images. So we start usually by defining our Python libraries. In particular, we import here from the science pipelines a way to get the tab service. This is going to be useful for the service. And then for this other, as I was mentioning, this Butler level interface that also will help us get the data as well. So we get that. Usually most, if not all of our tutorials start by defining um, an instance of the service and an instance of the Butler. In this case, it's just the name of the data we're talking about and what is called the collections, which is going to be the same for all the tutorials, in this case for DP1. And the first thing that we want to do here is to look at the schema. So in this particular query, we're going to use the tab service to demonstrate how to retrieve the schema for the DP1 object table. And here, we're actually gonna get this other, I guess, meta table called tab underscore schema. We're gonna get the columns from there. We're gonna get the name, the data type, description, the units, and then we would tell it what gives us the one for the object table of DP1. Here we're gonna be calling the service, and then this is the way in which we run the job in an asynchronous way, and then we use some error checking, and it worked. And we put the results in an AstroPy table when we do this two table function here. You can also get it in pandas if that's what you want. So there is a similar method. I guess you get a pandas table data frame. So we have now the schema. Of course, it has all the columns that I told you about, 1,300, which is a lot, but it shows you another way of browsing what you want. So one thing that you can do is, for example, if you can use some regular expression package, and if you know that you want something related to PSF flux, you have an idea of the type of strings that you're looking for, you can do a search here. And then again, this is another way of looking at the schema in addition to the website that I mentioned before and the portal aspect of the RSP. But you can do it here from the notebook aspect as well. So this is another example in which we're looking at the columns that have different strings of interest: error, pixel flag, composite model, tenderness parameter, and then you can get a subset that maybe makes things easier to decide on what kind of columns we want to get. This is notebook here, just is a self-contained, but it's related to what I was already saying before about out of those 1,300 columns, there are some that are of common interest, like the object IDs, a long integer. We have the coordinates that we recommend you use with associated errors. We have also photometry information, like magnitudes, different types of magnitudes, composite from PSF fitting, from composite model magnitudes, associated errors, other types of fluxes, C model fluxes. Then we have Sersic fluxes, gap fluxes, cron, etc., etc. The extinction that I was telling before, I was saying before, the extinction parameter, second moments for from the Hirata-Celiak-Mandelbaum method with some references if you want to take a look. One Boolean parameter that gives you a more or less a star galaxy separation, but if you have objects with extendedness of 0, they're more point source. If you have an extendedness of 1, they're more extended sources. So that gives you like a first order separation right there. And then flags. There are pixel flags, measuring flags, the blending flags that can help you decide on the type of cuts that you want to do. Okay, so here, for example, we can take a look. Again, you can do a loop here in Python to do a subset of the table that we recovered before to get a little bit more of the description of some of these quantities of interest along with the units and the type. That was for looking at the schema. Then for accessing the object table, as I was saying before, we recommend we can use the tab service and the butler, but we recommend using the tab service in principle to access the tables. This is again reiterating what I was saying, that is good to put a constraint, spatial constraints and columns constraints, because these tables are big and they're gonna get bigger with LSST as well. So yeah, this is saying something similar as well. So we can do here this demonstration query is gonna look for some of those key columns, the key columns from the previous section. We're gonna retrieve from the object table. We're gonna do our spatial constraint of being between 0.2 degrees of that Chandra's field center, and we're gonna sort them in an ascending way by right ascension. So we define the query, and then at the same time, we can just submit the job using the tab service that we define above. It took a few seconds, and then here we're getting the results in the right way. And then, of course, it failed. Let me see what happened. What happened there was maybe my internet is not being good. Well, let's try it again. Let's
Yeah,
see.
usually you just need to redo the fetch on this kind of error. It's just like a temporary
Use the
timer.
query?
Just the fetch part.
Yeah, let's see.
You don't need to redo and you don't need to restart the kernel. You just have to re-execute the fetch cell. And
Okay.
yeah, it was just like a temporary timeout during fetch.
Okay. Okay. Thank you,
Yeah.
Melissa. So great. We learned something. That is great. We always learn from errors. Um, so yeah, sometimes it's just a matter of rerunning again. Sometimes it's a matter of restarting the whole kernel, other types of things. But in this case, that's what it just needed. So the job completed. We redid the fetch. We put it in this results variable. We can take a look. So take a look. The numbers look reasonable. So that's nice. Uh, excuse me. We can then just plot some of that. We can look at the coordinates. We got the nice circle that we said that we wanted to query. And then, for example, we can do a plot of the error as a function of magnitude and see how it gets, it increases as the signal to noise ratio diminishes as the sources get fainter. Then we can also join tables. Of course, if you're familiar with SQL or the DQL, if you're not, that's fine. But one of the cool things that you can do is we have all these tables. Some of them have information that the other tables don't have, but usually there's a way of matching them. And in this case, it's going to be the object ID. And we want, in this example, we have the object table and we want to join it with the force source table that contains force PSF photometry in the processed visit images and different images at the sky coordinates of every object. So let's look at the query. So what's happening is I usually start from like, okay, from this object table, we give it the nickname O. We're gonna get the object ID and a PSF fitting flux in the R band. And also I want to join it. This is usually by default an inner joint, an intersection. So again, we're going to join it with this other table. We give it the nickname of FS, force photometry. And we tell it do the intersection or the joint by the object ID column in both of them. Then we do our spatial constraints, what we want the spatial constraints in coordinates. We're selecting point source like objects, and then we do a cut in magnitude as well, and a sorting, ascending or sorting by ID. So we define the query, we run the job via the tab service again. Takes a few seconds. It says it's completed, and now we're gonna fetch the result into a table again. And this is a query that gives us about 177 unique objects. So again, you can take a look if you want. And okay, yeah, it's nice. Okay, so we're gonna now show how you can access it with the butler. Then again, I said that tab is the recommended way of accessing the table, but sometimes the butler is a convenient way to retrieve all the objects in a given tract, for example. So we define the instance of the butler above. We call it butler. Then if you tell it the get dataset type object, then it's going to give us some information about what dataset type, how is defined. And then in particular, it's going to tell you these are the minimum dimensions that you need to give me if you want me to retrieve that object. And that's the sky map and the tract. So we can do another butler query in order to get the tract, for example. So we can define a query. We want to get the tracks that overlap with you only need to know the array and deck of the coordinates of what you want to do. So with this overlaps point is going to do the trick. So we're passing the coordinates of the field of interest, the Chandra field, and we get some object references that we're exploring here. The references have some data ID member, method or members, yes. And it gives us information about the sky map and the tract. So that's what we are gonna use to pass. Then again, please define the subset of columns that you wanna do. Don't get all the columns at the same time. And then once you have defined the columns in this list of columns, then you can just call the get method from the butler, passing the reference, the first reference that we got from here, from above. And that reference is going to contain this information that is needed to get that object. So, and then you pass the columns with the parameters keyword in this dictionary. Then again, you can look at the results. Then here in the tab service, we were doing already a constraints, but here after the fact, we can do our flags, our masking by hand. So we use just numpy where using defining the point like objects and with a minimum amount of flags or a maximum amount of flags. And then we did some filtering in our objects. So yeah, so we do a plotting of that, and that's like a basic way, a simple way of getting the object table. Okay, I wanted to show, I think I have 10 minutes, so maybe I wanted to show the survey map tutorial. I know, as I was saying before, another relevant tutorial for this is the deep coadds one. It tells you how to visualize the images, and I did that in the session yesterday, but I only had time to do that one. But another one is this one that is called the survey property maps. So let's do it. Maybe we'll have some time for a few questions. Okay, so looking very similar to our tutorials, and here we wanna learn about the type of survey property maps that we available. So these are available in hill sparse format, and they tell us information about, well, the survey. For example, the magnitude limit, the sky background, the sky noise, something called differential chromatic refraction, which is the wavelength dependence of refraction. Then yeah, we're gonna see. Then we have other types of here of survey maps with the corresponding definition. For example, the total exposure time accumulated per position, etc. So here we're gonna import what we need in order to explore these maps. We do the same as we did before. We're gonna use just the Butler this case because these maps are available just via the Butler for now, or I guess in general that's how it's gonna be accessed. So we define the Butler, we define the same field that we were using before, the Chandra, the center of the Chandra field, and then we can start using the Butler. The Butler has a registry associated to it, and then you can start querying the type of the data, say types of interest. For example, do a search with a regular expression here, and everything that you notice here, I guess it might be circular, but for example, if you know that these maps contain this string, then you says, give me everything that has this string, and then it gives you a list, this consolidated map, and it gives you a list of all the names, the objects that have those. So each one represents a hill sparse map containing the value of individual survey property. So we can uh, do like we did in the previous tutorial, get the data set type. Then it gives us the name of the object, the required dimensions, and the type. Then again, this method required, it just dimension dot dimensions dot required. It tells you the minimum amount of information you need in order to retrieve that. So the sky map, I think, is already defined where we define the butler, but here we're gonna tell it to guess to give us this particular map, which is like a PSF magnitude limit or a depth map in the R band. And then we got that hill sparse object here, and then we can just play a little bit around with it. So if you just look at it, then it gives you the type of parameters that help define this type of maps, like the end site and the number of pixels. You can evaluate the value of the property at a particular position, in this case, the center, and this is in units of magnitude, so it's the 27 magnitude. And here we can, yeah, your example at the map values at different arrays. So here we just different points at different locations on the sky. So here we're doing an array of locations and then just getting the values of the magnitudes at these different locations. So one thing to notice is that sometimes these maps, well, I believe that in general, these maps have like sentinel values for places like where there is no data or or if there's a position that is outside the region that the map covers. So in this case, is this ridiculously large or small value. Um, so it's something to keep in mind, but because, for example, if you want to get the statistics on the region of a particular region, then we're gonna have to replace those sentinel values with nans, for example, and then use like the NumPy functions that deal with nans in order to exclude them from the statistics. But this is what we were doing in this section. We're just replacing those values with nans, just something to keep in mind, and then calculate some statistics of this particular map. You can also visualize the map. So this is what it looks like when you take a look at it. And then you see the coverage. This is the best observed field of the 7 DP1 fields, is the one that goes deeper. This is a plot that is in one of the papers and in one of the technical notes of DP1, technical note Sitcom 149. And you can see that just take a look at the map. Then you can play a little bit around with it. For example, what we did here is just change the minimum and maximum values because I want to know the regions where the R band image depth is greater than 25 magnitudes. And then you can see, of course, that at the border is when it starts to fail a little bit because there's less overlap, but that's expected. So it's just the same map, but just plot it in different ways. You can play around with whatever color map you like. In this case, a gray color map. That's just is the same. And you can look at these Hilpers maps in a sky projection. So there is a package called SkyProj that it has very good documentation. I think you can take a look at it. Let me see. sky projection. Yeah, well, it has a really nice documentation if you want to take a look at it. But you can start doing projections there of these maps. And here we do a projection that it's you can see you can see the 7 fields here and the maps in of all these magnitude depth maps. But this is like a projection that is not taking into account the curvature of the sky, for example, and you can see for this on the lower right part that you have some extended field as the global cluster 47 to kind of. So, but you can, for example, look at the documentation of SkyProj and find other projections. There's a lot of projections that you can use, and in this case, we're using a different one called McBride Thomas flat polar quartic projection. And I guess it gives you something like this. Looks more reasonable. Um, so that's that to that this type of visualization of the maps. But then another cool thing that we can do is just visualize the actual image and and some of the property maps. So here what we're doing is using the butler in order to get to access the deep coadd image. This is something that is covered also in more detail in that other tutorial about deep coadds that I mentioned in the tutorial series. Here you go to data products, images, deep coadds. But we use the butler in order to find the deep coadd or the first to find the patch that contains this particular location on the sky, our central location. And then this query data sets is going to give us the references that have the minimum amount of information required in order to get the actual image, which then you pass that reference to the butler and it gives us the image. This object, this deep coat image that the butler gives you is gonna have metadata information, is gonna have a WCS attached, is gonna have a PSF model attached. And again, that's explored in more detail in the other tutorial. In this case, we're gonna be using the WCS, the astrometric solution. We're also getting the bounding box of the image itself in order to define the extent and the corners, the extent in pixels and then the corners in sky coordinates of the object. So I'm gonna skip this. This is just a visualization of the image because we're gonna see it later. But then now we wanna look at that image of that coad image with some of these survey property maps like the PSF size and the sky background map. So we remember the names that we retrieved above. Um, then we do a new grid that matches the boundaries of the image. And then we do a little bit of magic here, but I guess I'm running a little bit out of time. But well, we're substituting the pixels of sky coordinates as stick labels for the image. So this is just, we can plot things in sky coordinates. But then in the end, this last cell is gonna give us the what we want, which is looking at the image itself and then compare it with survey property maps and then maybe do correlations by eye. But it's always good to look at the data, of course. So this is nice to see different survey property maps, the PSF size, the sky background, and the depth limit correlated with the actual scene on the sky. Okay, thank you. Sorry, I guess I could answer a couple of questions if there are, but this is your 10-minute break, so feel free to leave. And um, sorry that I just ended on the hour. But I mean, please go to community if you have any questions, or come back for the questions for the Q&A session in a couple of hours. Thank you so much. I'm happy to answer one or two questions, and if not, we can go on a break.